We have a physics overload, and it's a little disturbing. Varun?
Yep, it's good.
We're on?
Yeah.
Anna and others, this is for you.
Hello.
Happy Thursday. Yesterday we just had a very short hour because it was part ACT day, and then we had a 20-minute class period, reading quiz, and that was about it. So, and we basically told jokes and made fun of you the rest of the time. So I didn't want to record that. So today, what I want to start with is a simple reaction. I want you to see what an electrochemical cell looks like. What do these things physically look like? How do they generate current? Well, if we take a simple redox reaction, did we see this yesterday? No. I thought we ran out of time. So, is this a redox reaction?
Yes. Yep.
How do you know that it's oxidation reduction?
Because one's reducing and one's oxidizing.
Yeah, because something oxidizes and something reduces. When we look at the oxidation numbers, Zn is 0 over here on the left, but then it's positive 2, so it got oxidized. And then the hydrogen is positive 1, goes down to 0, it got reduced. Recognize redox reactions. In this chapter, every reaction is a redox reaction. There's not one reaction that we'll see that's not redox.
Are these the first notes?
Yeah. This third line does not answer the middle line question here. How is this reaction described in terms of electron flow? The answer is that the zinc is releasing electrons, and those electrons are going to the hydrogen. That's the electron flow. If I have a beaker and I put some hydrochloric acid into it, now I have this. If I drop a chunk of zinc into it, there's going to be contact between the hydrogen ions and the zinc, and bubbles will form on the solid zinc, and they'll escape out. You'll see the zinc dissolving. What's inside of the bubbles that are forming on the zinc?
Nitrogen.
Oxygen.
Right, it's not zinc. It's not oxygen.
Hydrogen.
Hydrogen, look what's being made here. This gas is being made. That's what's making the bubbles. They're kind of accumulating on the bubble, and then they escape out. It's not zinc that is inside of the bubble. The zinc is dissolving into the solution. It's making the zinc plus 2 ion, which just gets dissolved in the water. Yes, ma'am?
So how come it doesn't have a charge?
Because it's neutral. It's a solid piece of neutral zinc. And as it reacts with the hydrogen, it gives 2 electrons to the hydrogens. Well, 1 each to the hydrogens. And then it becomes a positive 2. So it starts as neutral. Any solid piece of metal is neutral. And that's what I'm talking about. You're dropping a chunk of zinc into hydrochloric acid.
Is that because of how the electrons are shared among the?
Yeah. Because remember, in a metal, the outer electrons are kind of shared among zinc atoms. But yeah, those outer electrons do get kicked out. Yep. Okay, and then we have the bubbles of H2 forming. I want to bring your attention. Not yet. Just want to show you a brief sketch of what we believe looks like a cell. So electrochemical reactions are reactions in which we're going to take the thing that's oxidizing and the thing that's reducing and separate their containers. We're going to put the thing that's oxidizing into one beaker and have a second beaker for the thing that's reducing. Yeah. Yeah, this is good, and then we're going to add some things to it as we go. So if you're going to draw this, make it kind of big so that you can add things to it. What's up to you? I don't know that you need to write. I mean, we're going to do so much with these cells that you'd probably save yourself tonight. Yes, sir?
So, why is the platinum there? Is it just like a medium so that the electrons can go into the water?
Yeah, that's exactly right. It's an electrode.
Okay.
The zinc is oxidizing, so the electrons leave the zinc and they flow through the wire and then they come down. Now, we could just have the bare wire going into the solution, but we normally don't put the bare wire in. We'll put something that serves as an electrode that can get wet, that we can clean off at the end. Very commonly, platinum is used. Platinum is good for 2 reasons. Number one, it's a very good conductor, so the electrons can flow easily through it. the second thing into the solution where the reaction is going to occur. The second thing about platinum is it's a pretty non-reactive metal. Non-reactive meaning that we're not going to put the platinum in and then suddenly we're worried because it's dissolving on us. And so we have two reactions really going on. One of them is undesired. Platinum is a good inert metal. There's a major drawback to platinum though.
It's expensive.
It's expensive. We spent thousands of dollars on hunks of platinum so we could use them in our electrochemistry reaction. We don't have thousands of dollars to spend on electrodes. We use poor man's platinum.
Oh, palladium. No, that's even worse.
That's it's even more expensive.
Yeah, there's probably quite a cost for palladium too. I'll show you what we use.
Oh, should I move back there? Or
If you want to, or hand it to Nick.
Vic, I'm taking over. Yeah.
So I have some zinc chloride. This is the same essentially as the zinc sulfate that's in the picture. And so this is on the left, so I'm going to add some zinc chloride to this beaker. Don't stand in front of people, Nick.
Okay.
Oh, good. You want to squat down in the catcher's position, Nick? Maybe get those legs into shape. You're probably out of shape now.
No, I just caught open yesterday. It's good.
Okay. Then I have some HCl. That's going to be on the right side, the hydrochloric acid, providing the hydrogen ions, which will reduce. Okay. Into the zinc compartment, which is this one, I have a chunk of zinc. Now, it's been used a couple of times today, so it's kind of black on the bottom. It's starting to react and oxidize, and so it's turning black. But it is zinc. See, in fact, it's even stamped on there. You see that? Zinc. So I just drop that into the zinc solution. And then my poor man's platinum,
Iron?
a rod of graphite. You can get this for a fraction of the cost of platinum. And it's handy, too. Look at this. We can write with it. It's graphite. It's just the same as pencil lead. So that will go in there.
Is that nearly as conductive?
What's
Is
that?
that nearly as conductive? Or?
It does conduct very well.
Really?
Yep, it does. Not bad at all. All right, so I'm going to connect these two things, just as it shows in the picture, with a wire. I get these alligator clips on the edges of the ends of the wire. Oh yeah. All right. Now let's take a look inside of there. And if this reaction is going to run, then we should be able to see hydrogen bubbles on the graphite rod. See anything happening on that graphite rod?
No.
What is it missing?
We don't see anything happening.
Is it because there's no salty thing?
That's right. There's no salty thing.
You need a salt spread.
You're kind of a salty thing, Lena.
I'm salty. You're a salty thing.
All right, so what is this salty thing that you speak of? The salt bridge. No electrons are going to flow. If electrons were leaving here and going into there, that means that this would be losing all this negative charge and we'd have a buildup of positive charge in here. Solutions do not build up charge, ever. They can't. No charge ever builds up. Over here, the electrons would be flowing in. It would build up negative charge. That doesn't happen either. So that's what the salty thing does for us, is it's going to provide extra ions. So when the electrons leave, the ions will flow from the salt bridge into the solution and allow for the charge not to build up. So I have one of these. I think the book talked about this thing. What is it? It's a salt bridge, but what specifically is this salt bridge called? This is a U-tube. So that's what they're called, really. But it's not YOU tube, it's just a U tube. And that's going to serve as well as a salt bridge. I have made up some sodium chloride solution, and we'll use that for our salt bridge. I'll just fill that up. Now, the salt bridge with a U-tube is a little bit tricky because now this thing needs to be upside down, one end in this compartment, one end in that compartment. And what does that mean I'm going to have to do? I'm going to have to put my fingers over them, right, and then flip it upside down and put in one of those being hydrochloric acid.
It's okay, Mr. Williams.
It's okay. Just go ahead and do it, right? But I got Y's, and I have some stoppers. So I'll stopper both of these. Just loosely stopper them so that I can stick it upside down in there and then try to get the stoppers out. Drips a little bit. All right. A little bubble in there is not going to hurt anything. All right, so I stick those in there. And now I'll try to get the stoppers out. So I'll just take a end of a spoon. Now I am going to tell you, in this chapter, we're going to have a lab. There's one of them out. We're going to have a lab where I'm going to ask you to bring some materials in to try to make a battery. This is what is going to make a battery. And so that's going to be a battery lab. It's going to happen next Friday. You can use the YouTubes if you want to for a salt bridge. You will have to use a salt bridge. There's another issue with the YouTube. You get all that work done and then you do that. I lifted it up out of the solution, then I've just screwed up the whole thing. So I'm back to square one. Now another way that you can get the charges to remain neutral is to use something else. What did the book use?
Porous disc.
A porous disc. Right. What's the matter, Nick?
Huh?
You don't care about Anna?
No, I'm just trading off real quick.
All right, so I have a porous cup. With the porous cup, what you can do, here's my zinc solution, now with a little bit of salt water in there. I'll put the zinc solution in the cup, and then I will, I'm going to pour my hydrochloric acid into a little bit bigger beaker because it's easier to work with like this. So if I put the porous cup into, now the porous cup has the zinc solution, then the hydrochloric acid is out here. Now I'm going to take my poor man's graphite, or platinum, put that there, and this, and put that there, and now maybe, still nothing happening, great, oh there it goes.
Zoom in, Brandon.
So now if you're close to it, if you zoom your iPad in, you can see the little bubbles coming up and out of the end of the graphite. Oh, I mean platinum.
Just I don't.
So can you see the bubbling?
Yeah.
The little tiny bubbles. They're not much to see, but they're nice and cute and all that. And if we wanted to know what voltage this was, you know how we're talking about voltage in this chapter, we could do this.
Not seeing
We
the
could
book.
attach, rather than using this wire with the clips, we could use a voltmeter.
Zoom back, zoom back.
All right, now you can see that voltmeter jumps all over the place until it calms down. There it goes. Right now it says 0.00. If I touch one of my ends of the voltmeter on the zinc and the other one on the platinum, look at that. It shows a positive voltage. It's not a 10, it's just 0 point. So it's not a blow you away gigantic voltage, it's 0.73 volts or whatever. But this is the way that we will measure voltage, and we will run these electrochemical cells. We need the the ions to be able to migrate through the porous barrier so that the charges don't build up. And that's a electrochemical cell. That's what they look like, what they do. All right, let's come back up here. Nice. We're taking care of you, Anna, and others. Yeah, go ahead.
One method more effective than
The salt bridge versus the porous cup? No, I don't think so. I don't think so. They're both the same. I mean, you can imagine the porous cup. It would take a little bit of force to get the electron, or not the ions to go through those little holes in there. But once the porous cup, the pores in it are saturated, it flows pretty freely from one side to the other. All right. So the last picture did not have a salt bridge. This is an incomplete circuit. This is not going to conduct any current. But this will. Now that this, and it's the key word there is salt. You have to have some dissolved electrolyte in there. As the electrons leave the zinc and go over this way, we have a buildup of positive. So the negative ions come out of the salt bridge and flow into this compartment. The negative ions do.